Hello, I'm Catherine Stevens from the American Chemical Society. Welcome to this media briefing from ACS Fall 2021. We're joined today by Dr. Sara Hermann and Dr. Jessica Kansman from the Pennsylvania State University. They're protecting gardens and crops from insects using the smell of fear. Dr. Hermann?
Hello, everyone. I'm really excited to talk a bit today about the research we're doing in the Hermann lab at Penn State. Very broadly, we study insect ecology, which allows us to understand how insects interact with their environment or their ecosystem. In the lab, we're really interested in focusing in on a really specific element of insect ecology to understand how insects detect and respond to stressors. In particular, we've studied the stress that comes from the fear of encountering a predatory insect that wants to consume them. And so we call that the ecology of fear. Do you want to go to my first slide? So one really exciting part of this work is that it's really easy for folks to sort of understand in an intimate way the ideas that form the backbone of our research, because we as humans exhibit fear responses and respond to a myriad of stressors on a regular basis, whether that be work stress, climate change stress, or whatever stress you can imagine. While humans may not be facing predators per se, we do use our senses to detect and respond to threats or danger to avoid lethality. There's nothing about us that wants to get eaten or in trouble by something that's stressing us out. And these fear responses are really crucial in keeping ourselves safe. So for example, as we walk down the street, we can use our senses to first smell if something is a little bit off. Say we're going up to a building, but you start to smell smoke, or you smell something is burning. That's gonna put you on high alert. That's information that we use to integrate and respond to something that might be dangerous to us. But then if we couple that with seeing flames, using a different sensory modality to detect risk or threats, we're gonna respond by avoiding that fire. We're not gonna go into that building. And so we in the lab don't study humans, but the ideas and concepts of responding to stress draws parallels across the animal kingdom, including in insects. And so in the lab, we're really excited to understand how the fear of being eaten can influence behavior and physiology of these insects, and ask the question of whether or not predatory insects could be impacting the prey, and can we manipulate potentially that fear response, similar to how we use scarecrows to elicit fear and avoidance in birds. And so if we focus on understanding these dynamics in agricultural systems, where we've been actually harnessing the impact of predatory insects or these consumptive effects for centuries, we know that when we look at simple food webs like the one on the left-hand side, where you have a predatory insect on the top, it directly removes the herbivorous insects that is in the center. And by doing that, it relieves the pressure that that herbivorous insect has on our crop plants, which is something we really like as human consumers of food, and farmers really like for the sustainability of their operation. And so the question becomes, if we know that there are fear-based responses or potentially these non-consumptive effects, so the impact of predators without direct consumption, we might be able to use that in designing a sustainable pest management strategy. So non-consumptive effects is this risk of predation that affects prey. And by detecting this threat, you see the changes in behavior, life history, physiology of these insects that feed on crop plants, which alters their survival and performance overall. And so our goal in our early work has shown that these fear-based responses can change insect behaviors in ways that reduce their damage on these crop plants. We see changes in feeding, egg laying, colonization in these agricultural systems just in response to the predators. But the research that Dr. Kansman is doing in the lab aims to disentangle the way that insects are able to detect this risk and ask the question, could the smell of predators alert prey of danger? And can we use that to our advantage in crop systems?
Next slide. So we work in a very charismatic system of insects. We work with lady beetles or ladybugs and aphids. And so most people are quite familiar with ladybugs. And unfortunately, you might be familiar with aphids if you have a garden or if you have household plants, because they can oftentimes become a pest of even ornamental plants. But what people don't know is that aphids are present in nearly every crop that we grow worldwide. And they're a massive pest for a multitude of reasons. So one, they have this intense reproductive capacity where they clone themselves. And so their populations can reach incredibly high numbers in short periods of time. And two, they are also vectors of plant diseases, or they act as vectors of plant diseases. So much in the same way a mosquito can transmit viruses between people, so feeding on the blood of one person and then transmitting that virus to another person, aphids do that same thing in the plant world. So they're very devastating pests that we're always looking for novel and sustainable ways in which to manage them, which is why this idea of risk response is a really exciting concept in the system. Next transition. The work in our lab, as Sara has said, has shown some promising results. We're finding that aphids avoid plants with lady beetles on them and have fewer young in the presence of lady beetles. But the catch is, we're finding this in just response to the odor cues. So the actual beetle isn't on a plant that the aphid would be going to. In that system that I was showing on the left, this Y tube, it has air pumping into it from either a glass chamber containing lady beetles on plants or a glass container that has no lady beetles on plants. And we can put an aphid at the base of the Y and see which plant it would prefer to go to. And we're seeing that aphids are avoiding plants with lady beetles on them, which would be great for agricultural systems. You'd have less aphids coming into your plants or being on your plants, and a reduced risk of virus transmission potentially. In this other system, aphids and lady beetles were separated from each other with a barrier. So the only thing that was going between them were the smell cues. And we found that they had fewer young in that case. So this is a promising result for us moving forward. And so what we really want to do next is figure out how to bottle these odor cues in a way, how to understand what this smell of danger could be and the potential for an actual pest management strategy. You can go to the next slide. And so that's the work I've been doing in the lab as a postdoc. I've been trying to identify the smell of danger. So first, we're figuring out what lady beetles smell like in general, and then which of these compounds do aphids use to identify lady beetles? Are there specific compounds that we can piece together to form this blend that smells just like a lady beetle to an aphid and can elicit these behavioral responses or physiological responses that are ideal? And so to figure out what lady beetles smell like, we take volatile collections. So on the left here, we have lady beetles in glass container. There's one without and one with. And air is pushed through the top over the lady beetles and pulled out the bottom through a trap. That trap can be rinsed, and that solvent rinse can be put into a gas chromatograph mass spectrometer. And what that machine does is it separates out all of the individual compounds within the blend of the lady beetle odor profile. We can take that same idea and we can apply it in a way where we can puff those smells over top of aphid antennae. And so that's this electroantenogram that I have on here. So you can hook up an aphid with its antennae, which are the way aphids use to determine smells in their environment. It's like the nose of the insect. You can hook up the antennae to this device where it will test the electrophysiological response, or like an actual impulse response. The aphid is detecting something in its environment. So it can actually measure that response. And we can puff these different individual smells of the lady beetle odor profile over top of the antennae, figure out which smells are important to them, and then figure out what our whole mixture is going to be for this bottling the smell of danger.
Thank you, Dr. Hermann and Dr. Kansman. I'd like to ask you a few questions about your work. So why are new types of pesticides needed?
So as we're trying to feed a growing population, we are in need of increased crop productivity to a degree in which we haven't had to do before. And we're always on the hunt for new and sustainable pest management strategies as we're moving to reduce pesticide usage, since pesticides can be both have harmful impacts for human health as well as for beneficial other insects in our ecosystems like pollinators and other predators that we actually want to maintain. And so there's a need for these new types of pest management strategies, especially for growers that are working in organic systems or smaller scale systems where they might not have access to certain types of pesticides. So
as you guys explained, aphids are very destructive pest for home gardeners and for farmers alike. Do you know what their impact is on crop losses annually?
The impact is like in the billions. It's very hard to understand though, because of this impact. It's an indirect impact. So you have the impact of aphids feeding on crops, which is an issue in general. They're getting nutrients out of the plants, and it can cause them to grow smaller, and other factors outside of viruses. But then that indirect effect of viruses, it's incredibly challenging to quantify. But there's a lot of insecticide usage that is specifically for the management of aphids.
So how does the electroantenogram work?
So the electroantenogram is coupled typically with a gas chromatograph. So in the same way where the gas chromatograph is separating out these different individual compounds that make up an odor blend, and then allowing you to be able to identify the different compounds. This is also separating each different compound out and then blowing that compound, essentially in purified air, over top of these insect antennae. And the antennae are hooked up to an electrode that can detect that physiological response. So you're able to then not just blow one odor or one, the smell of a lady beetle over and see if the aphids respond. You're able to figure out which individual components are the aphids responding to.
So what type of reactions are you measuring in the aphids? Is it their movement or something else?
So with the EAG, or the electroantenogram, it's that electrophysiological kind of response. It's just an antenna response to a stimuli. So much more of a mechanical kind of response. But we're also, measuring all these behavioral responses as well. So whether or not aphids move towards something or not, whether or not they reproduce in the presence of a smell or not, attraction and repelling, those kinds of different measurements as well, coupled together, help you really understand what the impact is of those smells on aphids.
How many compounds did you identify in the odor profile of the ladybugs?
So there are a bunch of compounds. Like, this profile is actually quite large. There are a few that I'm particularly interested in at the moment because of their ecological impacts in general, what we know about these compounds already, because a lot of these compounds are actually existing in other organisms or even in plants. And so that we already understand a little bit of their function in these other systems, but we don't really know what their function is within lady beetles. So a couple of these compounds that are particularly interesting are, there's 3 methoxypyrazines that we've actually looked at, investigated a little further in our lab. If you smelled these 3 methoxypyrazines, you would know that that is what a lady beetle smells like. If you've ever had them in your house, you might be familiar. It's a very strong floral smell. And so these 3 compounds are characteristic to humans, in my experience, of lady beetles. But there are a few other compounds that are very characteristic in plants. This alpha pinene, we have humulene. These are plant terpenes that have various functions in plant defense. And then most interesting, beta caryophyllene has been present in these lady beetle odor profiles. And beta caryophyllene is well studied in insect ecology. And what's interesting to me about this is that it can act as an antagonist to aphid alarm pheromones. So aphids are also producing smells to communicate with one another if danger is nearby. An aphid can say, hey, watch out, there's a lady beetle nearby, with smells. And so this compound the lady beetle's producing could antagonize the smell. They've seen that in other systems, that it can antagonize the smell of the aphid alarm pheromone. So there's all sorts of interesting ecological outcomes that are coming from this research, on top of just figuring out what they smell like. It's the function is what's going to be an interesting step forward.
So you've done some lab work, and you have you been able to test whether this odor mixture that you've come up with will actually repel the aphids from plants?
So we have not gotten to that step with these compounds yet. But Sara has done some preliminary work with those 3 methoxypyrazines that we have that I discussed in the beginning. Sara, do you want to talk about that work a little bit?
Sure. Yes. So I have investigated the influence of that methoxypyrazine blend on aphid colonization in the field. And I found that there's significantly fewer aphids that come into a crop field when those odors are present. And it's a similar impact when you compare that to physical lady beetles being present on the plants. So we know that the lady beetles themselves are influencing whether or not these aphids want to come in, but that the odor blend also functions in that same way, that same fashion. And so we know that over a sort of short period of time in one system, and our hope is to explore that over longer periods of time, full growing seasons, and in multiple systems to see if we can really impact these aphids in a way that's beneficial for the plants.
And when do you plan to conduct field tests?
We have done some preliminary field tests with that blend of 3 methoxypyrazines that I mentioned earlier. And so we've seen that using those methoxypyrazines in the field, there is a reduction in aphid colonization to those plants in comparison to plants without. It's actually a reduction to the same degree as with plants that have actual physical lady beetles bagged to them. So that's a promising result that we're hoping to test in a field season this summer, looking at a longer term, like longer multiple week field season test of those blends and the effects on aphid colonization, in addition to other community members of the insect community.
That's great. So could these odors be sprayed onto fields, onto the plants themselves, or would they need to be diffused?
That's a great question. We are right now just diffusing these. These are volatile compounds, so they're dispersing readily in the field. And we are working with some companies to try to develop new diffusers that are more effective so that farmers won't have to replace the odors potentially quite as often, or so that they can disperse at a greater range. And so that's something that we're still trying to understand and work towards, but we have the benefit of working with these industry partners that have so many years of experience making diffusers for mating disruption, which is pretty widely used in lots of different crops. And so we're sort of leaning on that older research and that older discovery to bring this new idea to farms.
Yeah, that's the benefit of the work we're doing right now, is it's not completely coming out of nowhere. There's been a long history of using odor cues to manipulate insects in agriculture. So we're able to base off of some of these ideas, but just with a new angle or a new, new ecological concept to try to test.
That's great. So how long lasting would these compounds be once diffused? Would they need to be continuously diffused during the lifetime of the crops?
That is a question that we are investigating with some of Jess's research right now and with these trials in the other system on farms. The hope is that they diffuse over time and they stay efficient at affecting the aphid behavior, whatever pests we're trying to impact over the growing season. Jess, do you have anything to add to that?
Yeah, currently we've been using a 1-week replacement for the studies that we're doing, but yeah, that is definitely something that is investigated further, of how we are going to diffuse in the environment and how long can we how long can you leave these out? The less time that you have to change out something like this, the lower cost or the less work, so it's beneficial to have this as long lasting as possible. I'd imagine it would be an entire growing season type of product, but it could also potentially be deployed just when pest pressure is high, because it cycles throughout seasons of crop production.
That makes sense. Is it possible that these pests could evolve resistance to being repelled by the ladybug odor?
That's a really wonderful question. And it's something we think about a lot, because we obviously don't want to create a new strategy that then these insects can habituate to or get used to and stop responding to. I think the beauty of these compounds being very specific to these insects means that it's a real true cue. It's something that's not fake. It's something that's specifically about, for example, the lady beetle being there. There might be some shared compounds with other insects or plants, but that blend, that bouquet of ladybug smell is just specific to the ladybug. So it's an honest cue, and it's one we don't expect habituation to occur with. But the other nice thing about this system is that we also will get insects, predatory insects in fields where we're doing this work, which will cause consumption to occur, which causes aphid alarm pheromones. So there's the coupled effect of us putting out these cues, but actual predation also occurring that allows that cue to be even more honest. Like it smells risky, but it actually is also risky to be here.
Great. Could these odor molecules have unintended effects on other beneficial insects such as bees?
So that is a great question, and that's something that I am especially interested in with some of the field work I'm doing this summer right now. You know, what you don't want to have happen, since these lady beetles can eat other insects, they don't just eat aphids, they eat a variety of herbivores. So in some ways, this could be great because maybe it'll repel other herbivores other than aphids. So it could be even more beneficial than just to protect against aphids. But also these lady beetles are major predators. And so they are either out competing potentially other predators in the environment or even eating them. They are intraguild predators, we call that too. And so what we don't want to have happen is by putting out lady beetle odor cues, we're repelling other beneficial insects from an area that also might be worried about getting consumed by a lady beetle. So that shows the importance of having these field studies that look at whole community impacts and not just these isolated lab studies of the effects on aphids, because in the insect community, it's much more than that.
So to wrap us up, what are the next steps for your research?
So the next steps would be to take this new blend of the Harmonia, or this lady beetle odor profile, and try to apply it in a full-scale agricultural system. So actually mirroring conditions in which it would be applied for farmers as a product. So over the entire field season in a device that we can deploy to see the effects on aphids over the course of this longer period of time, in addition to the other members of the community in a real scale situation. The other applications of this project could be in different agricultural systems and different cropping systems, because aphids and lady beetles are ubiquitous across plants. So this could be applied in a variety of different agricultural crops, but it would need to be tested in these different systems to make sure that the effect is still the same and that the effect on the insect community outside of that is still the same. And in addition, we have a PhD student in our lab who's doing some really fascinating work with this system, where if we can, we use it as this push-pull mechanism, we call it. So you can push insects out of the crop that you're working in using a repellent odor, potentially this lady beetle odor, and pull them into an extra planting that you have around the border of your crop, or into another trap crop, we call, that is attractive to the pests. So you push them out of your crop, your major crop, into this border crop that then you can manage. So you could potentially use pesticides on that, or it's a plant that you're not actually worried about them consuming, but then you're able to not spray pesticides on your major crop that you are actually producing for products for food. So with all of these, there are so many different paths forward with this research.
Thank you. Media briefings for ACS Fall 2021 will be posted throughout the meeting at acs.org/ACS Fall 2021 briefings.